Hi everyone, and welcome to lab number 5, the last lab. This lab is probably the most fun one. I wish you guys could attend it in person and test the system yourself. Well, regardless, I'm going to try to make sure that everything makes sense. We have 2 exercises for this lab, for both of which we'll be using this pendulum setup, which will replace the disc that we used for the previous experiments. It is going to be magnetically attached on top of the servo motor. In the first exercise, we're just going to familiarize with it and change the conventions of the reading of the encoder. And in the second exercise, we'll design a PD controller to balance the pendulum in an upward position. Here we're going to go over some background for the first exercise, which is the modeling of the rotary pendulum. As you can see, the pendulum system consists of 2 parts. We have the rotary arm, which is attached to the motor pivot. The change of the angle for this arm is represented with the variable theta that we will use in the slides. And we also have the pendulum itself, whose angle is denoted by alpha. The pendulum and the arm are both represented in this figure. The convention that we use for the pendulum angle is that whenever the pendulum is facing up and it is in the upright position, the alpha value is 0. There's a slight difference between the way that we define this convention and the way that the readings are coming from the encoder. So when we're reading the position from the encoder, the pendulum angle will have a value of 0 when it is facing downward. In order to convert the pendulum angle readings from the encoder to this convention, we need to subtract the measured value by pi. We also use the remainder of the alpha full, which is the encoder reading, divided by 2 pi to make sure that the pendulum angle always falls between 0 and 2 times pi. In the first exercise, we want to just basically interact with the pendulum and read the encoder data and see if it is matching our convention, which defines a counterclockwise movement as positive, and also the upright position of the pendulum is considered to have a 0 angle. So this block diagram basically does that. The only new additions to this block diagram is first that we're using 2 output channels by changing the value of the channels tab in the settings of the HIL read encoder time-based block, and that we're using a radians to degrees converter. So I'm going to run this model and manually change the angular position of both the arm and the pendulum and see if the readings follow the convention that we have. So if I turn the arm counterclockwise, you can see that the measurements are less than 0, which is exactly the opposite of what we want. And also for the pendulum, well, first of all, when it is facing down, we have a value of 0, which is not what we want. And if I turn it counterclockwise, the value for it is going up and it is positive. So actually the readings do follow the counterclockwise positive convention. So next I'm going to add a few blocks to make sure that first of all the counterclockwise readings of the arm will be positive, and second that the pendulum angle will be having a value of 0 when in an upright position, and that it does not go beyond 0 or 360 degrees. So in order to make sure that the readings from the arm will have a counterclockwise positive value, I'm just going to multiply the value of the gain for the arm readings by -1. And in order to adjust the readings of the pendulum, I'm going to use 2 new blocks. The first one is the mod block, and the second one is a bias. So the mod block is just basically there to measure the remainder of a division of two values. So I'm going to define a constant equaling 2 times pi add it to the mod block, and also take the readings that we have straight from the encoder, and then I'm going to attach the mod block to the bias that we have, and the bias block basically adds a constant value to the signal that goes into it. Here we want a value of negative pi. And then I'm going to connect the bias block to the radians to degrees block. I'm going to run the model again, first building it. So let's see if the readings are now following the conventions that we have or not. First, I'm going to look at the angular position of the arm. I'm going to rotate it counterclockwise. As you can see, the readings are positive and increasing as I rotate the arm counterclockwise. And also for the readings for the pendulum, if I rotate it counterclockwise and into an upright position, you can see that it gradually approaches 0. I can also verify if the pendulum angle deviates from the 0 to 360 degrees range by rotating it more than one round. I can see that the value shoots back to negative 180. So in the next exercise, we want to vertically balance the rotary pendulum. So we'll be using a PD controller to balance the pendulum in the upright position while maintaining a desired position of the arm. When balancing the system, the pendulum angle alpha is small, and balancing can be accomplished with a simple PD controller. As shown in the figure, if you are further interested in keeping the arm in a desired position, a feedback loop from the arm position, designated by theta, will also be introduced. The control law can be expressed as follows. In this equation, Kp of theta is the arm angle proportional gain. Kp alpha is the pendulum angle proportional gain. Kd theta is the arm angle derivative gain, and Kd alpha is the pendulum angle derivative gain. The desired angle of the arm is denoted by theta r, and the reference for the pendulum angle is 0. That is why the proportional gain is only multiplied by the negative of the alpha value. We need to point out that the inverted pendulum system has inherently nonlinear dynamics, and in order to apply a PID controller, we need to use a linear approximation in the neighborhood of an equilibrium point, where in this case it is alpha equals to 0. Hence, the control law can only be applied for small angles of alpha for which a linearized approximation of the pendulum is valid. Here we used alpha less than or equal 10 as a threshold. So this is the block diagram for the PD controller, designed to keep the rotary pendulum at an upright position and also to keep the arm angle theta at 0. We basically have the same PD controller as the one that we had in lab number 4, but here we have 2 additional channels because we're controlling both theta and alpha. So there is a new block here that we're using. It's the switch. Switch enforces the small angle assumption that we had. So the switch outputs the control signal when the alpha angle is smaller than 10 degrees and returns 0 otherwise. We also have a subsystem here which applies the conversion of the encoder readings to radians in our desired convention where alpha equals to 0 corresponds to an upright position of the pendulum and counterclockwise rotation is considered to be positive. So as you can see, we have 4 paths that are summed up together in the end. The first path is for the proportional control term for the theta angle. The reference value is set to 0 and the proportional gain has a value of -2. The second path is for the derivative control of the theta angle and has a derivative gain of -2. The third and the fourth path correspond to controlling the alpha angle. The third path is the proportional control term with a gain value of 30, and the fourth path is the derivative control term with a derivative control gain of 2.5. So next I'm going to run the simulation. So as you can see right now, the pendulum angle is at a -180 degrees. So what I'm going to do is to rotate the pendulum so that its angle value falls in between the -10 to 10 range, and then that is when the control input signal is activated. So as I leave it, so as you can see, the angle of the pendulum is approximately equal to 0. There are a little bit of fluctuations and oscillations, but the overall behavior is around the point of 0. If I go and check the angular position of the arm, I can see that that has also a value of around 0. So if I open both of the plots and see them side by side, you can see that both of the angles are around the designated reference value of 0. Now if I try to rotate the pendulum so that its angle value goes beyond the -10 to 10 degrees range, the pendulum basically falls off, and this is because the switch turns off the control input. Okay, and as the last exercise, I'm going to change the reference value for the arm angle and rerun the simulation to see whether or not the system will be able to follow this reference value for the arm angle. So we have the scope for the angle theta here. Right now the theta value is at around 0. I'm going to have the pendulum enter the -10 to 10 degrees range and observe how the theta value changes over time. As you can see, it is moving down while still keeping the pendulum at an upright position. So in the end, the theta angle falls within 5 degrees of the designated reference value, which is 45 degrees. While it is in that range, the alpha angle is still kept around 0. So that was the last experiment. I hope this series of videos have been helpful for you. Thanks for watching, and goodbye.